Good afternoon, ladies and gentlemen. This is Hisung Yoon, and I will be presenting Chapter 11 Conclusions for Knowledge Graphs lecture. In conclusion, the book has provided a comprehensive introduction to knowledge graphs, which have been receiving more and more attention in recent years. Under the definition of a knowledge graph as a graph of data intended to accumulate and convey knowledge of the real world, whose nodes represent entities of interest and whose edges represent relations between these entities. And we have discussed models by which data can be structured as graphs, representations of schema, identity, and context, techniques for leveraging deductive and inductive knowledge, methods for the creation, enrichment, quality assessment, and refinement of knowledge graphs, principles and standards for publishing knowledge graphs, and finally, we have discussed the adoption of both open and enterprise knowledge graphs in the real world. And knowledge graphs have garnered significant attention not only from diverse organizations and industries, but also diverse search communities. This attention is due to the ubiquitous nature of the problem that knowledge graphs address, integrating and extracting value from diverse sources of data at large scale, be it in the context of a particular organization, community, or more general collections of human knowledge. The key insight of knowledge graphs is that graphs provide a simple, flexible, intuitive, and yet powerful abstraction for representing and integrating diverse data at large scale. This insight is far from new, but rather has finally come of age with the advent of knowledge graphs. Graphs have long been used to represent data and knowledge in areas such as graph algorithms and theory, graph databases, information extraction, knowledge representation, machine learning, the semantic web, and more. Graph query language. A variety of graph query languages are now available that, unlike other NoSQL alternatives, are fully featured, supporting not only the relational algebra, but also novel features such as navigational queries that can match paths of arbitrary lengths. A number of languages have been proposed for querying graphs, including the SparkQL query language for RDF graphs and Cypher, Gremlin, and gCore for querying property graphs. Underlying these query languages are some common primitives, including basic graph patterns, relational operators, path expressions, and more besides. The schemata, though graphs do not depend on a detailed relational-like schema to represent data. Various notions of graph schemata have been proposed in order to validate, summarize, and define the semantics of graphs. One of the benefits of modeling data as graphs versus, for example, the relational model is the option to forego or postpone the definition of a schema. However, when modeling data as graphs, schemata can be used to prescribe a high-level structure and/or semantics that the graph follows or should follow. There are three kinds of schema. One is semantic schema. A semantic schema allows for defining the meaning of high-level terms as known as vocabulary or terminology used in the graph, which facilitates reasoning over graphs using those terms. Validating schema. While semantic schemata allow for inferring new graph data, validating schemata allow for validating a given data graph with respect to some constraints. Emerging schemata. Both semantic and validating schemata require a domain expert to explicitly specify definitions and constraints. However, a data graph will often exhibit latent structures that can be automatically extracted as an emergent schema. Contextual framework. Contextual frameworks for graphs can be used to represent and reason about the scope of truth of knowledge in the graph, including various alternatives for reification, alternative graph frameworks, etc. While we could use the pattern of turning the edge into a node to directly represent such context, another option is to use reification, which allows for making statements about statements in a generic manner, or, in the case of a graph, for defining edges about edges. An alternative is to consider annotations that provide mathematical definitions of a contextual domain and key operations over that domain that can be applied automatically. Deductive form. Deductive forms of reasoning can be enabled over graphs using ontologies and/or rules, which can not only encode a machine-readable consensus about the meaning of the graph, but also provide automated access to implicit knowledge entailed by a graph through materialization or query rewriting. Ontology. An ontology is then a concrete formal representation of what terms mean within the scope in which they are used, e.g., a given domain. Reasoning. We can provide practical reasoning algorithms for ontologies that hold on any pair of input ontologies but may miss entailments, returning false instead of true in some cases. 2. always hold with the correct answer but only accept input ontologies with restricted features, or 3. Only return correct answers for any pair of input ontologies but may never hold on certain inputs. The algorithm graph algorithms such as centrality measures, community detection, clustering, etc. can be applied on the graph to gain insights about influential entities or edges, close-knit subgraphs of entities, and more. Besides, with graph parallel frameworks capable of applying such algorithms at large scale. Pathfinding aims to find paths in a graph, typically between pairs of nodes given as input. Various technical definitions exist that restrict the set of valid paths between such nodes, including simple paths that do not visit the same node twice, shortest paths that visit the fewest number of edges, or regular path queries that restrict the labels of edges that can be traversed by the path according to a regular expression. Graph techniques. Recent and continual advances in knowledge graph embeddings and graph neural networks have now opened up new possibilities for applying machine learning natively over graphs in the context of diverse texts, including classification, question answering, recommendations, and more. Besides knowledge graph embedding. The main goal of knowledge graph embedding techniques is to create a dense representation of the graph, i.e. embed the graph in a continuous, low-dimensional vector space that can then be used for machine learning tasks. Graph neural network. A graph neural network (GNN) builds a neural network based on topology of the data graph, i.e., nodes are connected to their neighbors per the data graph.
Rule and axiom mining techniques allow for extracting formal declarative hypotheses from a knowledge graph that encode high-level patterns and can be applied to derive new knowledge in a deductive, explainable manner. Graph-based information extraction can be applied to extract and/or enrich a knowledge graph from legacy sources of text and semi-structured data. Graph-based mapping languages facilitate integrating diverse sources of legacy structured data into the knowledge graph. Tools, techniques, and methodologies for ontology engineering and ontology learning can further guide the potentially collaborative creation of an ontology for the knowledge graph, encoding a consensus about its semantics and enabling access to implicit knowledge through deductive reasoning. Quality dimensions and metrics for knowledge graph allow for semantically assessing the readiness of knowledge graph for its investigated applications in both a qualitative and quantitative manner, where a variety of tools and frameworks are available to help perform such assessments. Knowledge graphs that have been integrated from diverse sources are likely to be incomplete or to encode incorrect data, where techniques and tools for knowledge graph refinement facilitate the automated completion and correction of knowledge graphs, thus improving its overall quality and usefulness. For the purpose of publishing open knowledge graphs, principles, best practice, and access protocols, as well as techniques for linking, licensing, access and usage control, encryption, and anonymization can be leveraged to maximize their potential impact on society in an ethical way. Research on knowledge graph involves a confluence of techniques from different research areas with the common object of maximizing the knowledge and thus value that can be distilled from diverse sources at a large scale using a graph-based data abstraction. While advances within these individual disciplines are sure to continue and to generate further impacts, particularly interesting research topics for knowledge graph arise from their intersections. The research topics and challenges that intersection occur are as follows. In the intersection of data graphs and deductive knowledge, we emphasize emerging topics such as formal semantics for property graphs with language that take into account the meaning of labels and property value, pairs on nodes and edges, and reasoning and querying over contextual data in order to derive conclusions and results valid in a particular setting. In the intersection of data graphs and inductive knowledge, we highlight topics such as similarity-based query relaxation, allowing to find approximate answers to exact queries based on numerical representations, for example embeddings, shape induction, in order to learn and formalize inherent patterns in the knowledge graph as constraints and contextual knowledge graph embeddings that provide numeric representations of nodes and edges that vary with time, place, etc. In the intersection of deductive and inductive knowledge, we mention the topics of entailment-aware knowledge graph embeddings that incorporate rules and/or ontologies when computing plausibility. Expressive graph neural networks proven capable of complex classification analogs to expressive ontology languages as well as further advances on rule and axiom mining, allowing to extract symbolic deductive representations from the knowledge graphs. Further challenges arise when considering the creation, enrichment, refinement, and publication of knowledge graphs, which call for further work on topics such as automated quality assessment and repair, distantly supervised extraction frameworks, efficient access protocols, and anonymization, to name but a few. Aside from specific topics, more general challenges for knowledge graphs include scalability, particularly for deductive and inductive reasoning, quality not only in terms of data but also models induced from knowledge graphs. Diversity is such as managing contextual or multi-model data, and dynamicity is considering temporal or streaming data, and finally usability, which is key to increasing adoption. Though techniques are continuously being proposed to address these challenges, they are unlikely to ever be completely solved. Rather, they serve as dimensions along which knowledge graphs and their techniques, tools, etc. will continue to mature. Given the availability of open knowledge graph whose quality continues to improve, as well as the growing adoption of enterprise knowledge graphs in various industries. Future research on knowledge graphs has the potential to foster key advancements in broad aspects of society.